Okay, so how is everyone today? Good, I hope? Not good, a little good. Both good and bad. All right, so then, there's an exam tonight. That's good, or bad. But at any rate, it's a fact. All right, so then let's continue. So, last time we were talking about the harmonic sequence and series. And in the first place, the sequence AN is 1 over n. AN is 1 over n. That's called the harmonic sequence. It's so important that it has a name. And when you try and add those all up, that's called the harmonic series. It's called the harmonic sequence. And the series summation from somewhere of 1 over n to infinity. So where do you have to start? From n is what? 1, right? You can't start at 0 because you can't divide by 0. So the series is called the harmonic series. So we said that the harmonic series diverges, and I was trying to explain why it diverges, and then I kind of like hit a roadblock really, because I couldn't. I was asking y'all if y'all see it, because I couldn't see it. I knew what it was supposed to work, but I don't know. Sometimes when you get up here in front of people, even if you're real good at this stuff, if you flub something, then it's hard to see it. So, well, the idea was that my claim was that you can get as many ones as you want, and that's true. So that part is true, but it's not very easy to see how you can get as many ones as you want. Okay, so instead of collecting ones, it turns out it's far easier to collect halves. So we're gonna collect halves. Okay, so then the terms in the harmonic sequence. So the harmonic series diverges because diverges because of the following. So we're going to add up all of the following. So 1, I'm going to say, okay, well that's already more than half. So I'll just take it by itself. And then the next term in the harmonic series, in the harmonic sequence that we want to add, would be half, right? And that's already half. So I'm just gonna take that as it is. Then what's the next one? A third, right? Now a third isn't a half, right? So I'm going to take another one. I'm going to take a fourth. But now here's the key insight. Is that 1/3 plus a fourth. That's more than half actually. It's more than half, because you could like just make a common denominator and what have you. You could do that. But notice, what if I just which one of these is bigger, a third or a half, a third or a fourth? Third. That one's bigger. So this, whatever this is, that has to be more than a fourth plus a fourth, right? Because I'm in some sense keeping that fourth and saying, I'll just round that third down to a fourth, and that's half, right? So in fact, that's half. In fact, more than half. Okay. So then now plus, what's the next one? A fifth. So a fifth plus a sixth plus. So now if I round both of those down to 1/6, then I'd have 2/6, right? and that's not a half. So I'll take another one and say a seventh. Now if I round all of them down to 1/7, that'd be 3/7, and that's not a half. So I'll take another one. If I round all of those down to 1/8, then that'd be 4/8. And because I'm rounding them down, in fact, that's more than a half. So that would be more than an eighth plus an eighth plus an eighth plus an eighth, which is a half. So now I've taken another half. All right, then we can just keep doing this now. So we can say, okay, a ninth plus a tenth plus an 11th. So this would be 3/11. That's not enough. A 12th. That'd be 4/12. If we do that same rounding thing, that's not enough. Plus what? A 13th. 5/13, not enough. Plus a 14th. That'd be 6/14. Not enough. And then we'd have a 15th. That'd be 7/15. Not enough, right? So then plus a 16th. And if we round them all down to a 16th, that's 8/16, right? So that's more than 8 times a 16th, rounding all of them down to a 16th, which is half. So do you observe that I keep taking a half? Now half's not real big, but like a billion halves is big, and right, half a billion. So if I can keep taking a half, then I can make the sum as big as I want, right? So suppose, the question is can I do this forever? Okay, the answer is going to be yes, but let's see why. So suppose that we, what?
So this is what I was saying last class when we were going to 1, where you just...
Yeah? You were saying to do this?
Yeah,
I just couldn't.
We were going to 1 where you just take it doubled, and as long as you have the number in the denominator in front of it, then since we have infinite to take from, you can always derive 1.
Well, if this were 1 over n squared, you wouldn't be able to do it. You wouldn't be able to collect enough of them.
The harmonic.
Yeah, but for the harmonic, it will work.
Yeah.
So then, suppose that we're in the tail. Suppose that we have the tail m more than 0, which is to say that suppose that we've cut off the first m terms. So that might be we cut off the first 10 terms. It might be that we cut off the first 10 million terms, or 10 billion, or whatever you like. So suppose we're in that tail, which is to say that the smallest term that we have to work with, the smallest one we have to work with, is 1 over m. So then we could have 1 over m plus the next one would be 1 over m plus 1, right? And then the next one would be 1 over m plus 2. Now if m is like trillions and trillions, then this is still pretty small. Okay, but we can go as far as we care to go. So suppose that we go all the way out to ... plus 1 over twice m minus 1 plus 1 over twice m. So if that was a trillion, then we went out to the 2 trillionth term there. Now suppose we round all of them down. we round all of them down to 1 over 2m. So this would be in fact greater than or equal to. So that's greater than or equal to. Rounding them all down to 1 over 2 to m. Two multiplied by m. So plus ... plus 1 over 2 m plus 1 over 2 m. Now the question is that how many of those are there? How how many are counted up here? Well, suppose that we started with an eighth, right? Then how far would we go out to? So we'd go out to 1/16th, right? If we started with 1/8, we'd go out to 1/16th. And then, you know, just counting, how many numbers are there, how many integers between 8 and 16 inclusive? In fact, 9. Because you gotta count the first one, right? So it would be 8, 9, 10, 11, 12, 13, 14, 15, 16. Wait a minute. 8, 9, 10, 11, 12, 13, 14, 15, 16. 9. Yeah, 9. Okay, good. So 9. So there's the quantity of these is there's actually m plus 1. There's m plus 1 of those. Okay. So then that means that that all would be equal to m plus 1 over 2m. And then, you know, we can divide in there. So that'd be equal to 1/2 plus 1 over 2m. So do you observe that in every tail, we can take enough to collect another half? So that means that we can make as many halves from the harmonic sequence that we want in the construction of the harmonic series, and therefore the harmonic series diverges. All right, good. So therefore we can always get another half. And therefore the harmonic series diverges. Diverges. All right, fine. So that's good. That's good information. The last thing that we said last time was is we were talking about something called a telescoping series. So specifically, if we say the following, if we say that let AN be a sequence, such that AN goes to 0. So that's just a compact way to say the limit as n goes to infinity of AN is 0. Now, AN might be negative some of the time, positive some of the time, positive all the time, negative all the time, but at any rate, its limit is 0. If we say that, let Bn be equal to AN, subtract AN plus, I don't know, I wrote like 8 last time, but it was too big, so I'll write 3. Now, there's nothing sacred about 3. That number could be anything. So suppose that we have that. Then let's find Sk, the kth partial sum for Bn. Well, S0 would be B0, which would be what? A0 minus A3. So A0 minus A3. All right. So then S1 would be S0 plus B1, which would be A0 minus A3 plus A1 minus A4. S2 would be S1 plus B2, which would be all that. So A0 minus A3 plus A1 minus A4, and then plus A2 minus A5. So notice that at the present time, all of the indices are unique, right? So 0, 3, 1, and 4, 2, and 5. There's no repetitions yet. But we do one more. We do one more, S3, well, that'd be S2 plus B3. So we have A0 minus A3 plus A1 minus A4 plus A2 minus A5. And now we have plus A3 minus A6. So now there's a repetition. Which index has been repeated? 3. And notice that it's been repeated with a sign offset, meaning with alternate sign, meaning that here we subtracted A3, but there we're adding A3. So in fact, those A3s cancel. Then the next term, we're going to say plus A4 minus A7. So we're going to be adding A4. That's going to cancel that subtraction of A4. So conceptually, what I want you to see is that here's what we're saying. We're saying that we're going to take A0 plus A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7 plus A8. Okay, I don't know if I'm going to put some dots there, but now we're going to start subtracting. So what is the first one that we subtract? A3. So then we're going to say subtract A3, subtract A4, subtract A5, subtract A6, subtract A7, subtract A8, ... So if we carry this procedure out infinitely far, which are the only ones that are not subject to being canceled? The first 3. So now, if I instead had written n plus 8, then it would be the first 8. If I had written you know, n plus 1, it just been the first one. All right. So all of this group is going to cancel. So we can say, therefore, the sum from I is 0 to infinity of Bn, which is, by definition, the sum from I is 0 to infinity of An minus An plus 3, we can say exactly what it is. What is it? A0 plus A1 plus A2. So that's the answer. All right. A big note here, because this often gets overlooked, or it can get overlooked anyway, is that this requires An has to go to 0. So you have to have that. Okay. So the place that this comes up is something like the following. So suppose that we have the sequence like this. Suppose that so this is me making an exercise back in my office. You wouldn't see this part. Okay. So then suppose that I say, oh, all right, I'm going to say that An is how about I don't know, 1 oh no. What do I want to do? Let's not make it too hard. So about 1 over 2n, like that. Okay, and then Bn, I'm going to say is going to be An minus A n plus 2. So again, this is me working back in my office, okay, making an exercise for you to work on. So I'll simplify this. That would be 1 over 2n, right? 1 over 2n, and then subtract what I want to do is I want to, substitute n with n plus 2, so that'd be subtract 1 over 2 n plus 2 like that. Right? And now, to muddy the waters as much as I possibly can, I'm going to simplify this expression. All right, so I can see that I could factor out a half. So I could factor out a half, and then it would look like this: 1 over n minus 1 over n plus 1. And, 2, thank you. And now I want to get a common denominator. So this would be half, right? And then the denominator, the common denominator would be n times n plus 2. And then I'd have n plus 2 minus n, right? So then that would be, that'd be what? 2, right? And then I can cancel the 2's. And I get the following: 1 over, and I'll go ahead and multiply that out, n squared plus 2n. Okay. So now here's the statement of the question. I could say, evaluate the sum from n is, I'll have to start at 1, from n is 1 to infinity of 1 over n squared plus 2n. So notably, I'm not asking if it converges or diverges. I'm not asking that. I'm saying evaluate it. Okay, which is to say that the question more or less is alleging that not only does it converge, but you can actually figure out what it converges to. So there's only so far for us, there's only 2 series that you can, yes? I'm sorry?
You have a 1 denominator, isn't it?
I canceled it. So there's only 2 series that you can evaluate exactly. There's the geometric series, that has formula a over 1 minus r, and there's telescoping series. So if I'm telling you evaluate this series, then by process of elimination, is this a geometric series? It's not, right? Because it's not a multiplied by some ratio like a third to an n. So it's not a geometric series. So sort of like by process of elimination, assuming that I'm not just utterly messing with you, this one must be a telescoping series. So somehow you must be able to represent this as a sequence where we're saying we've made a new sequence by actually taking a different sequence and shifting it a little bit, and we're just going to collect the first few terms, like maybe the first 8 or the first 2 or something like that. Now, if we're going to do that, that means that we need to represent this as a subtraction. So for all of those reasons, we're saying that therefore, we're thinking telescoping. And therefore, concerning that thing that we're summing up, 1 over n squared plus 2n, we must be able to simplify it and represent it as a subtraction of simpler things. So we want to take this composed thingy, and we want to decompose this fraction. Okay, good. So then, so we're going to do a partial fraction decomposition. So, in doing that, 1 over, you'd first want to factor it. So, oh, look, it factors as n times n plus 2 there. And then, according to the partial fraction decomposition that you learned, it is the case that the decomposition should have this structure: a over n plus b over n plus 2. And I'm going to elide the actual calculation because we've got to press on. But you can do that, and you would determine that this is equal to half over n, and then subtract or, you know, if you like, half. So add negative half over n plus 2, like that. So you'd figure out that a and b are half and negative half respectively. And then you can cancel or simplify these to get 1 over 2n, and then plus, minus 1 over twice n plus 2. And so what we're saying is that, oh, look, it's the difference of two things, and that one is a shifted one. So we could say let an be 1 over 2n. If that's the case, then what's that one? An plus 2, right? Then that is a n plus 2. And so what we were given, we can say as a result of these considerations, therefore the sum from n is 1 to infinity of that thing, 1 over n squared plus 2n, is actually equal to the sum from n is 1 to infinity of an subtract an plus 2. So it's telescoping. And how many terms are we going to collect? The first two. So the answer is, what is the first term? Is it A0? No, it's A1, right? So it would be A1 plus A2. All right. So then that would be what? Half plus a fourth. So 3/8. Beautiful. Yes?
How do we know to just call that a 1 over 2?
You mean this?
Yes.
Well, I'm just saying that that the general structure of a telescoping series is the sum from n is I'll just, to be like that one, I'll say 1 to infinity of an, and then subtract an, and then plus a shift. So I'll say plus k, like that. And so the answer is going to be a1 plus a2 plus dot 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 plus ak, however many there are. In this exercise, it was there was two of them. Question? Yeah.
On that step where you did 1 over 2n minus 1 over 2n plus 2.
This?
Yeah.
Yeah.
So if that is a, wouldn't that be n plus? No. If that is an, wouldn't that be an plus 4?
No, because here's what we're doing. So notice that what we're doing with the n is we're putting 1 in a numerator, and then 2, and then red box. 1 over 2, red box. So the match is whatever's in the box.
Okay,
so
the 2 stays constant.
Right, yeah. It's a substitution of this n for that, for n plus 2, yeah?
Okay, now as far as like your an minus n plus 2, the n, like the first term for the n, is it going to always be like a 1, like depending on the n equal 1.6?
No, I mean, in principle, it could be anything. Like just as an aside up here, you know, we could say, well, if you had this series that that looked like this, the sum from, say, n is 24 to infinity, like that, and the sum that we were doing was like bn minus bn plus 14, like that. Then because that's a shift of size 14, that means that we'd have 14 terms. And what would be the first term? 24. So we'd say that the answer would be, you know, B24 plus B25 plus ... So we'd, how far would we have to go? 38, is that right? That's not, is that right? I don't think that's right. So we'd have 2 terms here. Come on, brain. We have to make sure that we have 14 terms, right? So then, in fact, we do, if we do this number plus 14, that'd be 38, but that would actually be 15 terms. So we need to go to 37. So plus B 37. So that'd be 14 terms. You don't need to start at 1 or 0 or whatever.
Okay, so the number, when we say n plus 2, the 2 is going to, like, so what I'm trying to think of, like how many terms would we know, like,
Okay, well, I mean, let's look at it. So continuing it, do you agree that if we were to take A1 plus A2 plus A3 plus A4 plus A5 like that, then if we do a subtraction, if we did it like this, so subtract A1, subtract A2, subtract A3, subtract A4, subtract A5, you know, so ... So if we did that, the sum would be identically 0, because every term would cancel. So what I'm saying is that, well, what if we take all of the adds, but we cut off the first few subtracts? What if in particular we say cut these out? So we'll cut out those. So those are gone. So if we cut just those out, then do you observe that nothing's ever going to cancel the A1, A2, A3, and A4? Because we're starting there. So what that would be, writing it as a series, that would be the sum from n is 1, because that's where we're starting, to infinity, of an, and then subtract some shifted version of the sequence. So now, for those of you that are asking the question, I have to fill in the box. And the question is, what goes in the box? So what goes in the box?
N plus 5.
Which one's it going to be?
I'll say 4.
It's going to be 4. N plus 4, because look, this would be A1, the first term would be A1 subtract A5. A5 is the first one we're subtracting. A1 minus A5 plus A2 minus A6 plus A3 minus A7 plus. So what I'm saying is that if you take these and you remove the parentheses and you realign it so that it looks like this, so that we take all the adds and put them on the top row and all the subtracts and put them on the bottom row, and if we put this the subtract under its corresponding add, then from here on all of this will cancel. Wait, that's not cancel. Like that, right? All of that cancels. Okay? So we got to move to the next thing. All right. But the main idea is just, shift stuff. Take a sequence and shift it a little bit, and then make a subtraction. All right. Good. So some perfunctory matters. Some perfunctory matters is that first, is that the following statements are equivalent. It's not really that they are equivalent, but really better to say, yeah, I'll say it like that. The following are equivalent. The following are equivalent and both true. So first is that if the sum from I is, or n, I guess, since we've been using n, from n is 1 to infinity of an converges. So if it converges, it doesn't need to converge. For example, the harmonic series doesn't converge. So if that converges, that means that the limit as n goes to infinity of an is 0. So if then, if this, then that. Now you can logically turn around an implication like that. So calling the left-hand side P and calling the right-hand side Q. So this says if P then Q. We can negate, and when you negate all the things, then this converge changes to diverge, and this limit exists and equals to 0. The negation of that is that it either doesn't exist or it doesn't equal 0, one of those. And the implication changes from pointing to the right to pointing to the left. In the same kind of way that if you take an inequality and you multiply both sides by a negative number, the direction changes. Right? So then we could do that. And we could do this. We could say the sum from n is 1 to infinity of an diverges, or just generally doesn't converge. So now the implication points to the left, and that says that the limit as n goes to infinity of an either doesn't exist or it does exist, but it's not 0. All right. So now, you have to be very careful about the direction of the implication because it's not pointing both ways. So, for example, this is wrong. So if I say that an is the harmonic sequence, an is the harmonic sequence. So my first question is the limit as n goes to infinity of 1 over n. Well, that's about as easy as can be. So what's the answer? It's 0. So the limit of that sequence is 0. All right. But what does that say about the series, harmonic series? What I'm asking is that does this provide any information about that? No. This diverges for reasons that we've already stated. Right? So then what I'm saying is that notice for this first sentence that this side is true, but because the implication is pointing to the right, that doesn't mean that this is true. Similarly, let's see. What did I say? I said this one is true. So suppose that this diverges, doesn't exist or exists and isn't 0. Well, I mean, this one actually works for both of them actually, because now this one is true, that the series diverges, but because the implication is pointing that way, we can't conclude that. So the harmonic series diverges. But actually, the harmonic sequence, its limit exists and is 0. All right. So this is how this tool is used. It's used in the following way. We could say something like, just generally consider / determine if the sum from n is 1 to infinity of, how about n squared over 4 n squared plus 1 converges. So does it converge? All right. So here's the deal. If you have a series that converges, it must be the case that the corresponding sequence converges, and moreover, the corresponding sequence must converge where? To 0. So if the corresponding sequence either doesn't converge, or if it converges but it doesn't converge to 0, then the series can't converge. Okay? So what we're going to do, the first thing that we're going to do is we're going to check. Does the limit as n goes to infinity of an equal to 0? If the answer to that question is no, then the answer to the question about the series is also no. Okay, which is to say that if it converges, if it doesn't converge, or if it converges to something that's not 0, then the series diverges. All right. So the limit as n goes to infinity of n squared over 4n squared plus 1. Well, okay, so there's a variety of ways to proceed. So you could factor out n squared, okay, and do some algebraic whatever. Okay, and that might look like this. You could say, I'll factor out n squared and get n squared multiplied by 1 in the numerator, and then in the denominator, n squared multiplied by 4 plus 1 over n squared. And then the n squareds would cancel, so that you'd have the limit as n goes to infinity of 1 over 4 plus 1 over n squared. Right? And, well, what's the limit of 1? 1. And what's the limit of 4? 4. And what's the limit of 1 over n squared?
0.
So what's the limit of this thing here? It's a fourth. So if we wanted to add up all these terms, the sequence converges. That's good. But the sequence converges to a fourth. That's bad. Right? So then it's not going to work. So that's not 0, and therefore the series diverges. Because you can think of it like this. It's saying that if you want to sum up all the terms in a sequence, eventually those terms are going to have to start getting small if the series is going to converge, right? This is saying that eventually the terms start looking like a fourth. So eventually it's going to be just like you're adding up a fourth as many times, forever. And it's going to diverge. All right, but don't be misled. Because, for example, in the harmonic sequence, the terms go to 0. The sequence terms go to 0. Yet, it's not summable. All right, good. Any question about this? Yes?
May I ask, would it work the same way for that problem if we used the L'Hopital's rule?
Yes, it would work exactly the same. Because you could say, this is in the indeterminate form infinite over infinite. And then you could compute a derivative. Because, after all, the limit of a sequence is the corresponding continuous function, right? Like if you want to say x for a continuous variable, x squared over that. You can calculate derivatives, then this would be 2n in the numerator, and this would be 8n in the denominator, and then the n's would cancel, and you have 2 over 8 as a fourth. So L'Hopital's rule is just as good of a way. Other questions? All right. Good. Now we have to have a flashback to weeks and weeks ago. So this is section 11.3 there. This is the integral test. Now, here's the deal about integrals. What I want you to remember is that, remember, what an integral is that you're taking some area and you're saying, hey, I'm going to like estimate the area by cutting it into rectangles and then adding them up. And that gives me an estimate. And then the calculus battle cry is, you know, more rectangles, you know. And so we're going to want to end up adding up infinitely many infinitesimal rectangles. So what I want you to see is that an integral is an infinite summation. That's what it is. So it's, can you see that it's really closely related to what we're doing right now? Integral is saying add up all these things. And series is saying add up all these things. So there's sort of a connection there, and that's what this section is about. So if you'll remember, we had something back when we were doing improper integrals. We had something called the p-integral. Integral. So in particular, this is the p-integral. So it's integral 1 to infinity, and then 1 over x to p dx. So that's the p-integral. Now, in the specific case of p is 1, that's special, you know, because then the corresponding antiderivative is logarithm, right? So that one is special. But the rest of them, in some sense, can all be handled with the what am I trying to say? With the power rule. They can all be handled with the power rule. And what we said is that, in fact, we can compute this integral using the improper technique. Under what circumstance does the p-integral converge? When p is more than 1. So this converges when p is more than 1, and it diverges otherwise. All right. So now here's something that I hope is not surprising at all. Is I could say, well, if there's a p series, then there's a p integral. No, if there's a p integral, then there's a p series, is what I was trying to say. And now it's the sum from n is 1 to infinity of 1 over n to p. 1 over n to p. All right. So you know, this when p is 1, this is a series that we know by name. What is this series when p is 1? It's the harmonic series, which diverges. Do you have any suspicion about under what circumstance will the p series converge? When p is greater than 1. Okay, so this converges. When p is greater than 1, and it diverges otherwise. All right. So now, in the last 30 seconds, I want to give you the intuition of why this should be the case. So in the first place, we did this weeks ago. We did the p-integral weeks ago. And here's this new thing. Here's this new thing. All right. So if you plot 1 over x to p, this is 1 there, then 1 over x to p will look like this. Right? And then the integral from 1 to infinity would be all that area that's accumulated in there. Now, what if we cut this up into little regions like that have this size? So this would be 2, 3, 4, 5, etc. And what is, if we plug in 1, we'd get that height, right? And if we plug in 2, we'd get that height. If we plug in 3, that height, 4, that height, 5, that height. So those would be, in fact, that green is the sequence. And what if we just make a rectangle that has that height? Meaning their bases are all 1? Etc. Then the area of these rectangles that are peaking just a little bit over the top of the graph there. Now, that wouldn't be the integral, but actually, what is the sum of the areas of all those rectangles? That's exactly that, right? Because that's the height of the rectangle, and then the base is 1. So the integral is that area under the curve, and the series is actually the area of those rectangles where that little bit is peeking over. So the difference between them is just however big those little overshoots are. Okay, so first thing next time is we're going to talk about how big are those overshoots. All right, so have a nice exam tonight and weekend.